Welcome to the Universal Model, another class of exciting adventure today. Last week we had a pretty exciting time, something we only do a couple times a year. We had a conference where we had 7 speakers that spoke about the Universal Model. It was up in Sandy, Utah, and a couple thousand people came and got to hear about it and a lot of other fun topics. So that was a lot of fun. One of the things that I did on my opening presentation was I had a friend of mine come up. It was the first time I'd met him. His name was Bob Mell. Bob, I just want to give you a little story behind him. He was a geologist for over 40 years. He's 90 years old this year, 2021, and he's just been a fantastic support to the UN. When his story goes like this: when he first heard about the Universal Model, his son-in-law, a friend of mine, Ryan, actually, had told him about UM, and he politely said, "Well, Ryan, you've never really been interested in rocks and geology and stuff before. Why all of a sudden you interested in it now?" And Ryan tried to explain to him, "Now I understand it. I can explain how these things got made," but he wasn't really all that interested in him. And sometimes it takes by the mouth of 2 more witnesses for people to learn about it. So what happened was his friend who he works with is Rod Meldrum, a good friend of mine. He was a researcher. We worked together for 7 years. And Rod, he said, "Would you please talk to my dad? He loves your stuff that you've done already. And he just needs to hear from somebody else that's worked with Dean. The Universal Model is real and it's important." And he said, "Okay, I'll do it. I'll talk with him." So Rod was doing a tour, and on his way back, they had a couple hours, and he spoke to him for over 3 hours on the phone. And when he was done talking with him, he said, "Okay, I'll check it out. I'll read the Universal Model." So it wasn't very long after that Ryan got a call and said, "I can't believe this. This is revolutionary." What happened was he got so excited. He's read volume 1, the book you have, 5 times, and he's on volume 2, his 3rd reading of the book, on volume 2. And the reason you can read it like that and then read it over again is it's no different than anything that's true and real. Our lives change as we go along, and when we read something that we don't fully understand, because we don't have all knowledge, we don't have all truth. So when he had a chance each time to read it, I read it, and I learn something new every time I read it. Today we're going to talk about chapter 5, the Magma Pseudotheory. And in here, as I go through, every time there's new connections that I make that I didn't know before. And that's just the way it is when you're dealing with truth. So he was great. Bob was fantastic, and it was fun having him up there. He was very excited to share his story, and it's fun to see somebody that he has done actually petroleum geology all over the world, and he's had a chance to look at a lot of geological formations. And he said, by the way, he goes, "If I would have had this book when I was younger and learned this in school," he goes, my field of study would have been completely different. I would have understood where salt comes from, why it's next to oil. Nobody understands that today in modern geology." He goes, "Now I understand how these formations formed and how it was all from the universal flood." So he said this also helps strengthen his testimony, understanding that there is a creator. And this is all important part of each of us why we're here. So if we look here at the Magma Pseudotheory, it helps us. It says here, as we apply the question principle, so I'm looking in the 2nd paragraph here in the very beginning, to question everything with an open mind, to this chapter, the Magma Pseudotheory, and the upcoming rock cycle pseudotheory, it will allow us to present a number of extraordinary claims. Extraordinary claims are so important, or so extraordinary, that it requires all the textbooks to be written. How many textbooks do you think written today explain that magma is a pseudotheory? And one. This one. That's right. Very, very good. So you guys are already on track. I'm very impressed to realize that you have a chance to learn something that the rest of the world, both the kids and their teachers, don't understand. And that is what magma and lava really are. So over here on page 70 on the right hand side, we have definitions. As you go through the UM, you'll see in quotes and in green words, there's some that are bolded. And here we see magma is only a theoretical molten rock material. So this when it says theoretical, that means it's a theory. And remember, a theory is just an idea, okay, unless it can be proven. And we want to ask a really simple question. How many human beings have ever been to the center of the earth and seen magma? Zero, right? Nobody. So that's an important thing to remember. Then there's two types of lava there. One's extrusive and the other's intrusive. So one is that it has extruded out of the earth. That means it's manifested itself or come out of the earth onto the surface. That's your typical lava flow. Intrusive lava is the molten subsurface rock that occurs within the crust of the earth. And we're going to find out in just a minute here how that's all formed. So if we look down here under magma is only a theory, look at those bolded words there. It goes, well, we'll read that whole first paragraph. Because so much is known about planets that are light years away, one might assume that science has unearthed everything worth knowing about the one beneath our feet, right? So when you talk to astronomers and stuff, they will tell you, oh, we know about this planet or about this star, and the reason we know that is this and this and this, and they've never even been there, okay? Amazingly, in volume 3 we talk a lot about astronomy and how much astronomers really don't know. But here on the earth, when we can actually observe everything and put our feet on it and walk around, right, it's an opportunity for us to demonstrate the way things work. Look what it says in the bolded words there. To the contrary, Earth's innermost reachings remain in many ways as mysterious as the cosmos at large. Okay, so we had to look hard to find these quotes where we had honest authors talking about the magma pseudotheory because they don't like to tell us the truth. So as you can see here in the gold quotes right in the middle is one of the quotes. It says, magmas properly belong to the realm of theoretical petrology. Okay, so petrology is the study of rocks, and theoretical means it's only a theory. If we read down here on another bolded quote there on the left-hand side near the bottom, it says, speculations in the field are numerous, and these should be kept distinct from legitimate inference and proved fact. So see, the scientists really know that they are only inferring. By the way, the word infer you'll find through a lot of scientific literature. Infer means that, like up here at the top, it says, so geophysicists infer, since they haven't been to the center of the earth, they just have to infer. Are inferences as strong as physical observation? No, they're not, right? So that's the problem with inferring something. It's not real science, it's only a philosophy unless we can demonstrate it physically. Very important concept to keep in mind. We read down here in the bottom under a theory is taught as fact. These are, by the way, these black subheadings are sub-subs. So when I say sub-sub, then you know what I'm talking about here. A theory taught as fact. So that particular quote is a good one. We just read it already. Magmas properly belong to the realm of theoretical petrology. But then it says they are the most important concept in igneous petrology. So remember we're going to learn a little more about the rock cycle when we get to the next chapter. But igneous is one of the three types of rocks. Remember, igneous, metamorphic, and also sedimentary. Turns out all three of those we will change when we get to the hydroplanet model and learn how rocks are really made. Those three are all theoretical in what they do, talk. But it says they cannot be examined in the field and collected, studied, or directly experimented with. So that's the simple problem. Okay. And what we're reading about here, it's what is interesting is when you read regular geology textbooks, they don't emphasize this. They just gloss right over it and tell you that there's magma down there. So when we read the very end here, it says two facts are clear. They're on the bottom of page 71 there on the right-hand side. Lava can be observed and is real. So we know that lava is real, right? We can see movies on it. I've been to Hawaii, for example. You can actually see the lava coming out of there. And then in Italy, there's a lava flow there. It's pretty consistent. So we know it's real when we can see videos of it and people can observe it with their eyes. A lot of times you'll see the geologists, they'll stick things down into the hot lava and take some out for testing. When it dries, we're going to find out what it really is after it's been heated up. The right hand side, we have James Hutton. He's the father of geology, and also uniformity and the magma planet theory. The modern geologist will mingle truth with air all the time. Okay, all the scientists will do this when they're trying to prove a point. They'll take theories, and when they mingle them with facts, you go, oh well, I guess yeah, lava is something I can see, so I guess magma must be there too. Okay, and this is what they thought from the very beginning. There was a big. It was back before Darwin's time. He came out in 1859 with The Origin of Species. And before his time, actually, there was a lot of discussion about an igneous planet, okay, a planet that came from heat, or a Neptunism, which is a planet that came from water. And if you were somebody that believed in the scriptures and believed in the Bible, then you believed in Neptunism and then the water planet, okay? But it turned out over time, they weren't able to explain where this melted rock came that was coming out of the crust of the earth. And the reason is they didn't have sense enough equipment to recognize that every time there is a lava flow, before that, there was earthquakes. They didn't know that. They didn't have the seismic, which is the sound meters that are showing it happening all over the earth. So that is why today we actually have the technology. And when you have newer technology, it helps us understand things that we didn't fully understand before. So to answer your question of what's the difference between magma and lava and why would they be combining the two, it's simply that magma is the theoretical concept of melted rock inside the earth, and the lava is actual melted rock on the surface that we see. We're going to give in just a second, we actually have a new law here in a couple pages over that'll show how that lava actually got formed. Another thing that they have done is their whole purpose, magma, by the way, the reason the scientists like it today and they don't get rid of this theory is because it is used in their age theory. So the age of the earth and the age of man, they're millions of years, and the age of the earth is supposed to be 4.5 billion years, okay? That's all disproven in this book. Radiometric dating is taking rocks and dating them. And for that to happen, the rock has to be melted. So this is another reason why they want to believe everything was melted. The funny thing is, this is a piece of petrified wood here. You can see quartz crystals right in here, in the middle here, growing up. If you want to come up afterwards, you can see the rings going on here in the quartz crystals. Well, quartz is only formed one way, and that's out of water. And we know the pressure and the temperature that it has to be formed because we can make it in the laboratory. So that we know, and the paleontologists, the fossil guys, all acknowledge that there's no way these rocks were ever melted. So it's a quartz-based rock. When you melt quartz, it now turns to glass, and we'll be talking more about that next time we get together. But these concepts are all interconnected, so I don't mind, bringing them in, even talking about volume 2 and so forth, because they're all really interconnected. But this is the important concept, is to recognize that these rocks were never melted. This is a piece of copper ore. Now, most of you know what copper looks like, right? If you got a penny, on the outside of the pennies today, it has copper on it. Well, you have to melt this to get that copper look out of there, to get the metal out of the ore. Okay, this is from a mine out of Arizona. So this is one of the important things. Another aspect that came from the reason this age of the earth is important to them is that they don't have their millions of years, then they can't use evolution. Because see, evolution, we talked about this before, is one species changing to another. That's called macroevolution. And do we ever see a dog, which is the most diverse species of all the species on the earth, because it's been bred by people for thousands of years? Has anyone ever seen a dog turn to a cat? No. Okay. And so what they do is say, well, of course it hasn't, Dean. It takes millions of years. Well, no, it doesn't. Okay. So we've actually seen with bacteria that reproduce every hour, even every 30 minutes, tens of thousands of generations. Guess what they are after all those generations? Bacteria. So they don't change. Okay. And this is what's critical is there is no evidence for millions of years, period. And we will go way more into that in detail. But they need their time, and that's why they go back to having a magma planet, okay? The Earth's interior heat theory. We're going to get a little more into that. So James Hutton over here was also, gave us uniformity. According to Hutton, one need only observe nature as it exists today to understand all past events. He abhorred the idea of catastrophism, so which means catastrophic things took place. Originally, scientists accepted uniformitarianism as a way to defeat the idea that cataclysms had a part in shaping the earth. So when you read down through here, they're finally coming to understand today. They don't emphasize this uniformitarianism because this principle has been disproven. There's a lot of things that, for example, they think dinosaurs were eliminated from an impact, okay? Well, they weren't. We're going to explain that that was the flood that did that later on. But the main reason that James Hutton did not want there to be catastrophes in the past is he was not a Christian. He did not want the universal flood to be real. And this is the main problem with modern sciences. Most of the scientists are atheists, and they're not interested in hearing anything about any Noah, because who was Noah? He was a prophet. And a prophet does what? They testify of God, and they don't want that. So that's the bottom line why we don't have correct principles being taught like these, like there was a universal flood. They ignore all that evidence. So on the next page there in 73, we have the catastrophic principle. Major geological events occurred in the past, including processes that are not happening today. And one way we explained this was scientists thought, well, you know, if it was a comet that came by and affected the Earth, like Halley's Comet, then it would have come by every 78 years, right? Well, that's not the case anymore, because now we have comets that are over 12,000 years. Is a recent one that we talk about in the hydroplanet model. That means when the comet came by for the flood about 4,000 years ago, that we were able to show that it hasn't come by again. Okay, so now that we have, with new technology, we're able to show things that we didn't know about in the past. And that's, remember last time we talked about truth? What's the definition of truth? Truth is the knowledge of what is, was, and will be. Right. So this is what truth is, and it doesn't change. And you need a celestial body that's big enough to affect the Earth and slow down its rotation process. And it doesn't have to come by and hit the Earth, but just come close enough by, then you'll have that impact. Actually not hitting, but it will affect the Earth in a way that the plates will drop down and the water will come back out. So that's where the universal flood will, which of course we'll go into more detail later. So this is what the magma pseudotheory is. You can see from these diagrams here. We talked a little about this last time, that we know, scientists do know that the inside of the earth is liquid, okay? Why do they know what liquid is? Does anyone remember what this is here? What are they showing down here at the bottom? What's a seismometer? Hey, this is a sensitive instrument that when there's movement going in the crust, it senses it, puts a little ticker thing along the side there, and it measures several different kinds of waves. The S wave is the shear wave, doesn't go through liquids. And so when there's an earthquake up here at the top of the earth and it comes down, this core area is, because it's liquid all the way around it, the shear wave can't go through that. So down here on the other side is called a shadow zone, and it's an area that does not have any of the shear waves coming through. And so they've known this for quite a while now. For over 100 years, they've had instruments like this reading all around the earth. And so they know there's a liquid inside the earth. But the problem is there's only one large amount of any liquid in nature. And what's that? Water. Very good. So they have totally missed the boat because they think it's melted magma. So we only have time to go over some of the major concepts that are in here. One of them that we want to talk about, and it's really important, 5.3. So this is page 77 there, and you see in the red on the left-hand side, the law of friction model, okay? So now we're going to go into what a model is. Remember, a pseudo-theory is a false theory taught as fact, right? What is a model? It's a correct representation of what really is in nature. First off, we want to explain directly where lava comes from, okay? And then we're going to go into a little bit more like you're talking about. It's called heat flow physics, okay? And that's where we can show the gradient of heat and how that would have to exist. And also the reason why there should be heat inside the earth, okay? The mechanism for that. So if you look down here on the bottom of page 77, you can see raising the two hands being rubbed together. So what I like to do is have everybody take your hands, okay, put them together like this, and let's see how many you can do this. Okay, now I can already hear it there. I can already hear that isn't going to work. Just going like this doesn't work. Okay, you have to push it really hard together. That's the most important part, is having a lot of pressure, because I'm pushing over 100 pounds right now, and guess what? Guess what? Not only does it get hot, but look, you can see skin lava right on my hand. Can you guys see that? Not everybody can do it, but you have to press it really hard. Usually right here on this part of the palms is where I rub mine, and it kind of get just that part right there together. Go back and forth, and look, then it comes out. You can see skin lava, right? Well, what happens is when you have 1,000,000 pounds of pressure, not just the little bit you're doing there, but in a fault line, there's a lot of rock. Rock's heavy, right? And so all that rock pushing on that with 1 centimeter movement, a centimeter is just that far, okay? So it takes 2.5 centimeters to make an inch. That much movement, and the scientists explain that there's literally tens of thousands of degrees that it makes heat, okay, when you're rubbering two things together like that. So another question I like to ask people, well, why is it hot in the center of the earth? If it's really hot, why? Someone has to be able to explain. Remember, the explanation is the wisdom, okay, of how and why. So why would it be hot inside the earth? If it really is hot, why? And well, number one answer I typically hear from people is, oh, it's a lot of pressure down there. A lot of pressure, right? Well, what happens when you take a vise and you put something in there, a piece of paper, or put a nail or a piece of wood, and you crank it really tight? Does it get hot? No. You have to have pressure and what? Movement that gives us the friction, right? We know when you take a drill and you go on a piece of wood, okay, and you can actually start a fire, right? If you take another piece of wood and rub it on another one, back and forth, and get it really hot. Exactly, but that's movement, and it's going against pressure, so there's friction involved. So if you look on the page at bottom 78 there, you can see this line of red. You see that going along there, that line? Why is it long and thin like that? The lava flow that's coming out. Along a fault line. I heard someone say that. That's right. It's because it's along a fault line. And this diagram up here shows you what's going on underneath the earth. It's not very easy to go down there and take a picture, is it? So we actually had to make a diagram and show you that. But this is what's taking place. And because there's water all over inside the earth, when that water hits a heated fault line, what does it do? Turns into steam. That's right. And it tries to find the lowest pressure, and that's what causes it to come up. And this is how you get hydro fountains. Okay, so if we look over here on page 79, yes, on page 79, we see a really important diagram. Look down at figure 5.3.5. So that 5 means we're in chapter 5. 5.3 means subchapter 5.3. And then 0.5 gives us the particular diagram that we're in. That's what those numbers mean on there, okay? 5.35. And you can see here, you read right below that, it says earthquake swarms, volcanic eruption diagram showing over 600 earthquake swarms occurring during or to volcanic eruptions. So, this is one thing that I was really glad to find about, a little bit of history about the UM. Whenever, as researchers, I'm able to go in and find another scientist that has actually done what I was planning to do, which was to go out and find lava flows and then look at places that had the seismic registers there in place, the meters that would have registered that, it would take me a lot of work. It would take years for me to go out and find every time there's an eruption that, oh, here's the seismic and showing that there was an earthquake before the eruption. But guess what? I was blessed because here was an individual that already did that. He measured over 600 different eruptions, and you can see all the areas on here. I took his information and put it on this graph. The important thing to recognize is these are even bigger eruptions. So when you have a 4 or 5 earthquake, if we had one in this area here of this town, everything in here would start going like this, okay? And this could even fall off the table like that with a 4 or 5, okay? A 6 is even way serious. This building would probably crack and fall apart because it's an older building under a 6. And a 7, every time you go up from one number to another, it's 10 times more powerful. So a 7 is 10 times more powerful than a 6. I've been in a very minor earthquake a number of years ago. How many of you in here have ever experienced an earthquake? Wow. Was it here in town or where? Oh, one in Salt Lake. So that's interesting. You guys had a chance to hear that. Most people don't have that chance as much. Well, there's going to be more earthquakes that are happening, and it's very unnerving because if you're in one that lasts for a while, everything underneath your feet is moving, and you normally feel like you're walking on solid ground, right? So earthquakes are a very interesting situation. As you can see over here into this diagram on page 80, it shows you what volcanic structures look like, the different kinds. Up here, they actually take two metals that are different kinds of metals, and they can weld them together by frictional heating. So the technologists have found out about this. They know frictional heating is an important thing. So on page 81 on the left-hand side, the frictional heat law. Frictional heating produces lava from pressure and movement in fault lines. Look how simple that is. So all your natural laws that you'll find are cause and effect laws, okay? There's an effect that comes from a cause. So the cause here is the frictional heating, and the effect is lava is produced, okay, from the pressure and the movement and the fault planes. So that is a simple, easy law for us to find. And remember how many years we talked about this last time we got together? How many years it's been since there's been a natural law in science discovered? Over 100 years. And look how simple that is. How easy it is for modern science to understand this. If they will just get rid of their bias and say, look, we don't have observation for magma. There's no mechanism to heat magma. We're going to talk about another mechanism they like to use, radiometric here. Hopefully we have time for that. So over here on the right-hand side on page 82, we talk about the earthquake eruption cycle evidence. So when you read through quotes through here, you'll find, like this one down here in the middle, in February 2000, violent eruptions at Etna's southeast crater were occurring at 12 and 24-hour intervals. Ooh, 12 and 24, what's that mean? What do we know happens every 24 hours? It's a new day, right? 24 hours and 12 hours. That's the cycle of the Earth to go around, okay? And that's why we're getting earthquakes are connected to the lunar cycle. So the moon takes 27 days to go around. So it moves very slowly going around, but we go around just in one day. So this is why you have these cycles, and the sun, of course, takes 365 days to go around. So this is why it's important to recognize the cycles. And to this day, scientists don't understand earthquakes. Amazingly, they don't understand where they come from and how they're connected to the celestial bodies around us. The earth breathing evidence there on bottom of 82. You guys ever considered the earth's breathing? What do we call that? Say it again. The tide, but it has a special name. It's called earth tide. So write that one down, because this will come up over and over in our discussions. Earth tide is a really important concept. It helps us understand a whole bunch of things. And they don't teach this in modern geology classes because it doesn't fit their paradigm. But if you look over here on this figure 5.39, it says below it, the gravitational tug of the Earth and the sun, not magma, causes moonquakes on the moon. See, so the moon has moonquakes, and that's why they're happening there. And the same thing with earthquakes on the Earth. This is happening because of the gravitational pull back and forth. One thing to keep in mind is we all know about tides in the ocean, right? And what's pulling on the water? The moon, right? And the sun. Both of them are pulling on the tides of the water. Does gravity only pull on water? No, it pulls on everything, right? So that's helping us understand that it's pulling also on the crust of the Earth. And the modern geologists know that the crust is floating. Well, for something to float, what does it have to be on? On a liquid. And what's the only large amount of liquid in the universe? Water, exactly. So that's what the crust is floating on, is water, and that's why it's everywhere below our feet. So we have the solar cycle evidence. There's just a bunch of really neat evidences in here. The rock burst tidal evidence, the Juan de Fuca ridge tidal evidence. So each one of these sub-chapters are evidences, and you can read from the scientists themselves. You guys all know what the blue words are, right? That's their quotes from the scientists themselves. And you can even go to the little note section down there right afterwards if you want to read more about the quote and find the page online that talks about it. So there's geyser tidal evidence. This is an easy one probably for you guys to understand. Everybody know what a geyser is? Where do you see a lot of geysers erupt? Yellowstone. What's the second most occurring place? No. There are some in Montana, though. Yellowstone is in Wyoming, and right next to Montana, by Bozeman, where my wife's from, actually. But guess what the second most active place is in the world? No, not Russia. I went there 2 years ago, and you couldn't go there during COVID. No. No, Australia, Iceland. She's a little bit of a cheater there because she know I went. But that's all right. Iceland is the second most active place in the world for these geysers where the water shoots out of the ground. Now, the reason this is important is that water's heated, okay? And it's coming out because guess what's underneath the ground? Friction, okay? And you can see, well, oh yeah, so we go over here on page 88. Here's Yellowstone National Park, and you can actually see one place there. There's a little V spot. So if you actually, I've looked on other maps, it actually shows 3 places that there's fault lines, and they all come together in one spot there. And all these fault lines coming together in one close area is why Yellowstone has so many geysers going off there, and why you smell the sulfur when you go, because sulfur comes from bacteria. Okay, this is growing in the hot water, and this is where this all takes place, is inside the ground. So we have up here on the top of page 86 the gravitational friction law. There's another natural law that is not difficult to understand. The frictional heating in the crust, that's the effect. Remember, cause and effect for natural laws. That's the effect, is caused by the gravitational pull and release of the crust by other celestial bodies. So another celestial body would be the moon or the sun. Okay? It's not difficult. It's very simple. Okay. The ring of fire. If you look at figure 5.314, you can see the ring of fire. Down at the bottom there on the left-hand corner, you see volcanoes, little red a triangle. And then look at the little black dots. Those are the earthquakes. Do you see a connection? What is all those little black dots? You notice they're actually showing you with the little black dots there. You can actually see the plate boundaries. And then, of course, on top of those little black dots, which are the earthquakes, is what? All the major eruptions. That's what the little triangles are. So the ring of fire is around the Pacific Ocean, and you can see how the major lava flows that occur are all along the fault plains. Okay, so let's go over here to look at Io on page 89. This is a real important concept to understand. You can see in figure 5.316, page 89, the little diagram there. Io is a moon, and it's an important moon of Jupiter. You can see over here on this side a diagram. We have the actual moon of Jupiter, and there's actually, looks like there's a little eruption going on the side of it. You can see there right on the edge there. So there's several other moons, Castello, Ganymede, and Europa. These are all the 4 biggest moons of Jupiter, okay? So Io is important because it's one of the closest to Jupiter. So this is what's important, is the scientists already know this. They know that the largest lava flows, I mean, this is taken, this lava flow they have a picture of here is an actual picture from a satellite. So we are flying a satellite around this moon, and when we fly satellites around the Earth and they take pictures down, guess how many lava flows they can see from the picture? 0. That's important to understand, because the ones on Earth are not as big, near as big as they are on Io. Why is Io's lava flows so big? A lot of gravitational pull going on, right? So on Earth, I didn't explain this before, on Earth we have about where we're at right now in Utah, about a 1-foot movement, okay, of our crust. In 24 hours, our crust goes up and down, meaning this building, the mountains around us, everything goes up and down, about 1 foot in 24 hours. This is Earth tide. That is measured by satellites, okay? So when I go to move my phone like this, it can tell you, oh, you're going north, oh, you're going east. that happens, just that little bit of movement, because the satellites can actually measure down to a millimeter of movement. It's very, very important. Well, next time we talk, we're going to be talking about their theoretical concept that the crust of the Earth is falling, or moving up over time, over millions of years. And we disproved that completely by showing it when they went to Mount Everest and put a bolt up there on the top of it, and they came back year after year and measured it. Guess how much it moved? Zero. So the mountains are not going up and down over a long period of time. What they're doing is, well, they're not going up, or down, 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 down. That's not happening. The ground just shifts up and down. It's basically like your lungs for breathing. That's what the Earth's doing, is breathing. So back to Io. On the Earth, right here in Utah, we have about a foot. On the equator, you have about 2 feet. Okay, that's the little foot mark there. When you put one little thing like that, that's 1 foot, 2 feet. At the equator, because the crust is more movable down there, it's being pulled out by the rotational spin of the Earth. It goes out and back in about 2 feet. But here's the important thing. Io's surface goes up and down. What's M stand for? Meters. That's about the size of a yard, right? Almost 300 feet. 100 meters. There's a quote there that I can find it. Matter of fact, on page 90, the top blue quote says, "Here the gravity of Jupiter and large moon Ganymede, with the help from moons from Europa and Castello, play tug of war with Io, playing the part of the rope. Io bulges on 2 sides like a football. So it's pushing it in and out. And it literally, if you look on the very bottom of page 89, the right-hand corner, solid tidal bulges, this is from NASA, on Io are about 100 meters high. That's taller than a 40-story building. So that's how far the crust is going up and down, okay? And by the way, Io's day, ours is 24 hours. I think Io's day for it to turn around is only 7 hours, if I remember correctly. So that is a lot of movement, and that's why there's so much melted rock on the surface of Io. All right, so on page 90, 5.4, magma theory defies heat flow physics. So we want to talk a little about physics here and heat flow. If you look down at the bottom here, you guys are all familiar with a kitchen, right? And a stove. And if you have water there and you're boiling it, okay, there's 2 types of ways that that water is going to get heated. It says there conduction and convection, okay? So convection is when something's turning around like this and going in a circle. Matter of fact, we'll talk a lot more detail later on about how we make rocks in an autoclave. But in our tall pipe, we heat the bottom more than we do the top. And what does heat do when you heat water and you heat fire? What does it do? It rises, okay? So heated material like gases and liquids will rise, okay? And then it cools down when it gets up, and so it falls, okay? So rises and falls. This is the convection thing that's going on and laying down the quartz inside our autoclave and making rocks. And it takes a little bit of time for that to go on, and in just a couple days you can make a quartz rock. And you can make sand in just minutes. They're very small little rocks. But talking about here, what we want to talk about right now is conduction. So conduction is a way you can see conduction is, right now in this room, we have light coming through a window over there. So you feel that what the temperature is in here. What happens if I go put my hand on the window where the sun's shining through? Is it going to feel cooler or warmer? Warmer, okay? As if I have a stove and it's 300 degrees there and I'm standing this far away, as I get closer and closer to the flame, maybe coming off a gas stove, it's going to get warmer and warmer as you get closer, okay? So conduction is a real important concept in physics, and when you when you get farther and farther away from a heat source, it gets cooler and cooler. So I want you to look at these two maps down here. One of them is the actual heat flow on the right. This is on page 92. And on the left is the theoretical heat flow on the left, okay? So the one on the right is the what actually happens. And if you look there, see where the fault lines are, where the red and the orange areas that are going up and down? That's where all the heat is coming out of the earth. This is actual, okay? And this is what's amazing is they don't show you what the theoretical side should be. This is on the left side. I had to make this map on the left side to show you if heat was really coming out of the earth, this is the way the map would look. Notice how different these two maps are? Are they anything the same? No, they're completely different. The way we made this map over here is we use their colors. The blue is cool and the yellow is in the middle and the red is the hot, okay? And then you look up here at the top on figure 5.4.3. By the way, parents and kids both, if you want to read the quickly and understand it before you go in and start reading all the words, just read this little figure description right below an image. Okay, that's a summary of what's on the page. So it's real easy. Any of you in this class, doesn't matter how young you are, you can read these little figure descriptions and look at the image and you can understand what we're going to be talking about on that page. Okay? So this one, crustal thickness, shows you how thick all the crusts are. You see that big brown area up there in Greenland and over here in China area. The brown area there, do you know what that is? It's a mountain range. Okay? That's the Alps. Okay? Very high mountain range. Over here where we're at in America, you can see the Rocky Mountains a little brown there and down in South America. Okay, you can see along Chile area there. So this has a crustal thickness, not only above the ground, but underneath the ground, it's like a carrot. Okay, you got a mountain going up and then going down underneath the continent. So the continents kind of look like carrot going underneath the ground and then mountains coming up on top. It's crystals is really what they are. Our crust is crystalline, made out of minerals that have crystallized and grown out of water, by the way. But anyway, we took this crustal thickness map and we said, okay, the thickest parts, it's like if you have a coat on, like she's got a pretty good insulated coat on there right now, okay? So when the heat's coming out of your body is about 98.6 degrees right now, right? Okay, but in this room, it's probably only 70 degrees. So you have heat coming out of your body. If you put an insulated jacket on, you're holding that heat in. That's why you stay warm. Okay? So this same thing's happening down here on the earth. The really thick areas should be where it's insulating and keeping the heat inside the earth from coming out. Okay? Just like a jacket holds all your heat in. The really thin areas, if all you have is a little thin like this, my 98.6 degrees is going to go right through my shirt, right through. But if I got a big thick jacket, it's not going to be able to come out as easy. So down here we showed that, and all where the thick areas of the crust are, the continents, they're blue. That's the way they should be, because that should be just like a big jacket, keeping all that heat down inside and not letting it out. And then down here where you see all the red, that's the thin areas of the crust, okay? So this is all assuming the inside of the earth is red, and as you can tell, it's completely opposite, okay? Proving that the magma heat flow physics doesn't work. Okay, if you turn the page and look on 93 here, you can see now we go to the scientists. So I had to make this diagram over here to help show everybody. But we actually go to the scientists themselves, and what do they show us here? These two diagrams that we made, they have numbers that we've put in here. There's the theoretical magma heat flow, okay, which shows you from the crust, just like it's an insulated coat, it keeps all the heat down inside here. It should only be 5 degrees per centigrade per kilometer. So that's the flow rate, okay? For every kilometer of length, it's how many degrees it should go up. And then over here under the thin crust, that's where a lot of heat is being let out. That's like a really thin jacket of mine or a shirt that's letting a lot of the heat out, where a big heavy coat on over here would keep it in. So this is the way theoretically the Earth should be if there was magma down inside. But now we go down here and we see the actual numbers. These actual numbers are 25 degrees Celsius per kilometer is coming out of the crust, and only 15 degrees Celsius per kilometer is coming out of the crust. These arrows are exactly the opposite of these up here. Just the opposite. And these numbers, as you read the description down here, you'll find in the blue quotes on the pages. We don't have time to read through them all. But this is the scientists themselves indicating that there's more heat coming out of the crust that's on the continents that's really thick than there is in the oceans. Now, why would that be? Why would we have more heat coming out of the crust and it not insulating us from heat underneath us? Where does heat come from? From friction in the crust, exactly. Do you see why it's coming out of the continental crust there? Because that's where the rubbing's taking place, the earth tide. We just talked about it here, right? Every day, it's 1 and 2 feet, the ground is moving. And that's what's causing the heat in the crust line more than it in the continental crust, because it's the thicker areas. Okay, so the predicted magma thermal conductivity and thermal gradient variations are not consistent with the Fourier law. So that is a quote up here in the gold letters on page 96. Very important quote, because the Fourier law explains, like we said, if you have a heat coming from a stove and as you get farther away, it gets cooler and cooler. It's real simple. That's what this law explains, but guess what? That's not what's happening on the Earth, because they think heat is coming from the center of the Earth, and instead it's coming from the continents, where all the rubbing's taking place. Okay, 5.5 is the accretion theory. In a nutshell, basically, you can see in this picture here, I had my researcher, he had to take a whole bunch of pictures to take that actual one. When you hit a billiard ball into other balls on the table, they don't all just clump back together. They spread apart. So accretion theory is and it's a really dumb theory, okay? They think out in space that rocks just hit each other and then they all heat up and they make a planet. Makes no sense. Okay? And we show later on me hitting I had eggs that I used from chickens in my backyard. I had a golf club, and one of the researchers explained, yeah, trying to say that rocks come together and make a melt is like hitting an egg with your golf club and be able to send it far away. It doesn't work. None of the physics works for their theories. Rocks coming together and heating and melting and creating a molten earth. Nobody's able to demonstrate it in a lab or any type of model to ever be real. The same thing with the radioactive myth. Can you see right here? I'm holding in my hands. This is what they call yellow cake. These yellow rocks are radioactive rocks. Okay? Is my hand melting? You know how hot you have to get for rocks to melt? Quartz takes 2,400 degrees Fahrenheit or 1,700 degrees Celsius to melt. That's very hot, 2,400 degrees, okay? So those rocks are not 2,400 degrees. They're just the same temperature as any other rocks. The only way you get uranium from radiometric rocks, this is a Geiger counter I have next to it, and it's going tick, 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 telling you these are radioactive. Now, I don't want to leave them on my hand or put it under my pillow for a long time because it would give me cancer in my hand, because there is radioactivity coming out of the rocks. But for them to get uranium, they have to process thousands and thousands of tons of this ore, and then they have to chemically process it just to get a little teeny piece of uranium ore. Well, not ore, but uranium metal. If you hold that piece of metal in your hand And that's man-made. We're going to talk a lot about this in the chemical model, volume 3. That's man-made metal. It's like aluminum. You don't find in nature aluminum anywhere, or even steel in nature. It doesn't exist. And especially uranium does not exist. But it's barely warm to the touch if you have it in your hand, and that's a man-made one. So thinking that radioactivity is melting rocks in the earth is a complete fallacy. It's dogma. Dogma means that it's something that they just teach over and over, but it makes no sense. So we ask an important question here on page 99. Where is the radioactive lava? My wife and I met when we were in BYU, Hawaii. And I like to ask people the question all the time. So do you think my wife and I, when we were dating and we're walking down the beach together, holding hands, were we wearing our radioactive suit or bathing suits? Okay? Because Hawaii is all lava. Okay, that's where it came from, as from out of the ground. So if radioactivity was hot down underneath the ground, if all this melted rock down there was melted by radioactivity, okay, those rocks would still be radioactive today. You guys have heard of these nuclear reactors. There's one in Japan that tsunami came in there a couple years ago and caused killed thousands of people, and the radioactivity of the plant got compromised, and that caused the heat to get dispelled. And the point is, the people had to leave that town and can't to this day go back because the radioactivity hasn't gone away. Okay, so that's really important to recognize. If the ground inside was melted by radioactivity and now it came up on the surface, all that rock that my wife and I were walking along the beach, okay, would still be radioactive. And I'd have to wear my radioactive suit to protect me. We didn't. We wore a bathing suit. Over here we have a picture of the inside of a nuclear reactor, okay? And the same thing with these rocks here. It's not something you and I can see. It's like a radio wave. Okay, we'll talk about energy more later. Modern science does not know what energy is. They also don't know what matter is. They don't have an incorrect model on both of them, and that's what the study of physics is. So they have no clue. Physicists have no clue. We actually have the correct models, and that's a chapter I'm currently working on for volume 3 right now. Microorganisms, we talked about this before, are through all the they're in pipes in when they made the first nuclear bombs. The place they got the uranium ore was out of pipes that was by the Grand Canyon. So by the Grand Canyon, there was hydro fountains that blew up and came out of the ground, and that heated water inside there, when you have the right microbes, produce the uranium ore. And from that uranium ore, they get these high energy rays coming off the rock. So that's all we have the time today to explain about that. The important part is that they're not hot, okay? And also, when you go to lava flows, you don't see signs like this one here on the bottom of page 100 that says, danger, danger, radioactive lava flow, right? We don't see that anywhere. So next time, we want to encourage all of you to be reading 5.7 until the end of the chapter of Magma. We're going to talk about quartz is not glass. Thanks for coming.